Hello and welcome to today's problem 124 binary tree maximum path sum. So a path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connection connecting them. The node can only appear in the sequence at most once, and it also doesn't need to pass through the roots. So the path sum is the sum of the node's values in the path. Given the root, return the maximum of any non-empty path. Okay. We're given two examples here. We have 2, 1, 3, and we're given 9, negative 10, 20, 15, 7. The output for the first example is 6 because the optimal path is 2 plus 1 plus 3 equaling 6. And the optimal path for this one is 15 plus 20 plus 7 because adding all those together produces the highest number. Okay, just to verify this, we can walk through, let's say like 9, negative 10, 20, and 7. That'll be negative 1. That'll be 19. And then this will be 26. So that's a lot less than 42, which makes sense because it's not the result. Okay, so I kind of have a sense of the problem now. To break it down into how we're going to solve this, we'll take a look at different scenarios in order to find the maximum path sum. So the way I think about path sums is where you start from the root. We'll start at 3, and then we kind of go down to the leaf node. We'll have like negative 10, 20, 7, adding all of those up together in order to figure out what the final value is, and checking to see whether or not that's the maximum. However, the definition of a path in this scenario is pair of adjacent nodes in the sequence has an edge connecting to them, which is why a valid one could be 15, 20, and 7, or even like things like 9, negative 10, 20, and 7. Another valid one could also be 9, negative 10, 20, and 15. So, okay, so let's go ahead and put that down into writing. So we have the first approach for finding a path sum. We take a look from the top or like from here, and then we determine like go down, and eventually you split between like let's say for node 20, if you go through the method that I talked about from before, we go 9, negative 10, 20. Eventually you'll have to come across a point where you split between 15 and 7. So in this case, what we're going to want to do is we're going to have to choose between that. So choose between left and right. Now, the second approach I can see is if we're starting from 15, and then we completely have to we can disregard this, and then we'll go ahead 15, 20, and 7 and check it from that way. So we can go ahead and write that down. So start at left, and then splits between current node and traverse to the right over here. So knowing that there's these two approaches, we can figure out potential ways of calculating this and comparing to see what the maximum is for this. Okay, so one way of traversing through a binary tree would be using a DFS. So what potential way we could do this is we could do a DFS and figure out what the maximum is the maximum of the left and the right is as you traverse it. So doing this will allow you to figure out what the actual maximum of the whole problem is we're going to need a results variable which keep tracks of what the global maximum is in this problem, and then we can traverse through down through in different ways, checking to see what the maximum is and comparing between the left and the right to see what their maximums are. So yeah, we'll go ahead and code that one up first. Another thing we have to watch out for as well is the second one where you start at the left and you split between the current two. For that one, what we're going to want to do is calculate the maximum if you were to add the left, the current value, and the right value together for that one as well. So yeah, so to keep things a little bit simple, let's go ahead and code up the first approach first. So we'll start off with a DFS. We'll have the results array we'll set that up to the root.val, and then we're going to want to return the result afterward. Then we can write a DFS method taking in a current value, and then call DFS on the root. Okay, so since we're going to be doing a DFS and manipulating the results value, the nature of Python is that integers are immutable, meaning if you try to change the value of different of the res as you're recursing through the DFS, then unless you mark it as a non-local variable, then you'll run into issues. So another way to bypass this in Python, which I think is a simpler way, is by making this into a list over here, and then whenever you want to manipulate it, you can just return the 0th index of that. So we'll go ahead and do that. The next thing we need to do is just run a regular DFS, calculating what the maximums of the left and the right are. So we can do left max equals DFS on the current one, left max, what you call a DFS on, current dot left, right max, where you call a DFS on the right one, and from there, we also need to make sure that we need to account for scenarios where there aren't any nodes, or like the current value is none. So we're going to want to do if not cur. If that doesn't exist, we want to return 0. Now, why do we return 0? At the very end, we want to return the path sum, and like if we reach a leaf node and the empty values here should count as 0, it shouldn't be adding anything to the final results one. So we'll go ahead and do that. And then the next thing we're going to want to do is we're going to actually want to return the current value with the maximum of the left and the right. So this way, if we come across an area here, we go negative 10, 20, and then we have to choose between 15 and 7. We'll choose the maximum path of that every single time. So yeah. Another thing we also need to watch out for is scenarios where we do have to split it. Let's say we have 15, 20, and 7 here. We want to be able to choose this path as well. So we'll go ahead and set the result 0 to account for this. So we can do that by checking to see what the max is of the current one we have as 0, as well as the maximum of the current val plus the left maximum plus the right maximum combined. Okay, so since we're doing this, we also need to account for any values which are negative, because those would end up detrimenting the calculation itself, and detrimenting the maximum value itself, and it would be better to omit it altogether. So in order to prevent that from being calculated as a possible maximum path sum, what we can do is we can figure out the max of the DFS of the current left along with 0 to make sure it's non-negative, as well as the max of the DFS of the current right to make sure it's non-negative as well. So this way, the left and the right max will always end up contributing to that final path sum in the very end. So yeah, we're really doing the crux of the calculations over here. This one calculating the scenarios where it's 15, 20, and 7. You add in the current value with the left maximum. Let's see, we're at negative 10. We're adding in the left maximum, which is 9, and then the left ones, which also calls recursively on this and this. And then we'll also be doing the equivalents for just all their scenarios like that. And for this one, this is a more straightforward approach. You have negative 10, 20, and then we either choose between 15 and 7. And yeah, so that's where most of our calculation is coming from. Yeah, so, and this should work correctly. We can run through an example with it again. We'll go ahead and run DFS on the root negative 10 over here. First things first, we check to see whether or not there's a current. There is. We calculate the left maximum of this one. This ends up being 9. And then we calculate the left maximum of this. This left maximum, the DFS method is called over here. We check again with the left maximum, the right maximum, and the result over here could also be the split as well, 15, 20, and 7. And eventually we'll come across that it's 15 plus 20 plus 7, which is the result, and that adds up to 42, which is what our final value will be. So yeah, we'll go ahead and run this to verify that it's working correctly. It's accepted. We'll go ahead and submit. All right, there you have it.